Hey, good morning, kids. We're ready to do what is probably one of the top three hardest topics in the class, which is intermolecular forces. And it's a difficult topic because it makes you combine several things that you've learned about in the past along with some new material. You have to be able to correctly come up with a covalent Lewis dot structure, and from that, find the molecular geometry, and then use your knowledge about bond types to come up with what kind of intermolecular forces are going to be present within a molecule. So it requires a lot of synthesis of knowledge that we've had in the past combined with some new stuff. So let's dig into it. The first thing to consider when trying to arrive at the type of intermolecular forces present will be your bond type. So let's do some review on that. Remember, you will be given the electronegativities for the atoms involved in the bond, and you'll be finding the difference. If the difference is between 0 and 0.3, you're going to be considering that nonpolar covalent. If it's greater than 0.3 and less than or equal to 1.7, you're going to consider it polar covalent. And if you are greater than 1.7, you're going to be considering that bond ionic. And let's look at what's happening to the electrons in each of these three bond types. For nonpolar covalent, the electrons are shared equally. So you can see in this picture, here are the two electrons involved in this bond. Because the electronegativity difference is so small, the electrons are going to be equally shared, spending 50% of the time around this atom and 50% of the time around this atom. Since they're equally splitting their time, there are no partial charges on either of the atoms. The exact opposite of that situation is going to be ionic. Very large electronegativity differences, so much so that there can't be any sharing of the electrons. There's just complete transfer or taking of one electron from one atom to the other. So this electron is now spending 100% of its time around one of the atoms and 0% of its time around the other atom. This results in full charges and ions, so a full positive here and a full negative here. In between is polar covalent. It's sort of ionic bonding light. The electronegativity differences aren't quite as great, so there's still some sharing, but the key thing here is unequal sharing. So these two electrons that are being shared between hydrogen and chlorine are being shared unequally. Chlorine is the more electronegative atom, so the electrons in this bond spend more than 50% of the time around the chlorine atom and less than 50% of the time around hydrogen. This results in partial charges. A partial positive for the lower electronegativity atom, because the electrons are spending less than half the time here, and a partial negative for the higher electronegativity atom, because the electrons are spending more than half their time here. Okay. We also need to consider the structure of each of these. So in ionic compounds, we refer to these as formula units, which is the simplest whole number ratio of ions in a compound. So here would be zoomed way in on a salt crystal, and we see that for every sodium atom, sodium ion I should say, there's one chlorine ion. So our formula unit would be NaCl. Other things, the formula unit might be other ratios of whole numbers, but it's always going to be ratios of whole numbers of ions. And we don't refer to these as as molecules because they're arranged in what we call a crystal lattice, which is just this repeating structure of positive, negative, and it could be extended into whatever size crystal you wanted to make. So there isn't any one molecule, so to speak, of sodium chloride. Instead, we have a sodium ion experiencing attraction for all the neighboring chlorine ions, and there is no one molecule. It's attracted to all of its neighboring ions, and that could be extended out to any size. So this is just a bit of semantics. I'll try not to say molecules when I'm talking about ionic compounds, but instead refer to them as formula units. Covalent compounds, on the other hand, have definite beginnings and endings, so we get to refer to these as molecules, and the numbers in that is not the simplest ratio like an empirical formula, but just however many of each type of element there are in one of the molecules. And like I said, we get to talk about these as being separate from each other. So if I have a molecule of carbon dioxide and I have a second molecule of carbon dioxide, there isn't any bonds between these two. There's not any attraction or anything. These are two separate entities. So when we write CO2, that's because that's what's actually the number of atoms of each element in that molecule. Okay, so now on to kind of the meat of our discussion, which is the intermolecular forces. And it is the attraction between molecules. A lot of students confuse this with the strength of the bonds within a molecule. That's not what we're talking about. We are talking about molecule A compared to molecule B. Is there any attraction between them? Ionic compounds, in the strictest sense, don't have intermolecular forces because they don't have molecules. But it's important to notice that the attraction is very strong within all the ions present in an ionic compound because of their opposite charges. So I'll say intermolecular forces when we're talking about these. Like I said, this is sort of a semantic thing. You just need to associate these with having very high attraction, so high intermolecular force, even though that's not technically correct. And that's because we have full opposite charges, and the opposite charges attract. Nonpolar compounds have very low intermolecular forces, low attraction between two separate molecules, because they lack any charges. So there isn't a positive charge and a negative charge on neighboring molecules to attract each other. Polar covalent compounds have intermediate intermolecular forces because they have partial charges. It's not as strong as the full charges in ionic compounds, but it's definitely stronger than the lack of any charges in nonpolar covalent compounds. So these partial charges we're going to refer to as dipoles because there's going to be two poles involved, a positive pole and a negative pole. So you'll see this term show up as we continue on into the PowerPoint. So we have strongest, medium, and weakest kind of intermolecular forces. Before we delve any further into what actually gives rise to the intermolecular forces, I want to take some time just to compare some properties of ionic and covalent compounds that are caused by the intermolecular forces. And the first one I want to talk about is brittleness. Ionic compounds are very brittle because moving the crystal just one atom's width will cause a misalignment of the charges, and you will experience repulsion instead of attraction. So if I draw a very quick crystal lattice here, and you were to hammer on this and move this so much as just one atom, now you're going to have like charges being aligned, and that's going to create repulsion. So ionic compounds are very brittle because they need to be held in this rigid crystal lattice in order to maintain their attractive forces. Low intermolecular forces in covalent compounds allow the molecules to move past each other very easily. So this makes nonpolar covalent compounds very soft, with polar covalent compounds kind of an intermediate between the very, very soft nonpolar and the very, very brittle ionic. The next property I'm going to talk about is melting and boiling points. Anytime you melt or boil a substance, you increase the distance between the molecules. So if there's a very high attraction, there's a spelling mistake, if there's a very high attraction between them, this is going to be more difficult, which results in you having to increase the temperature further in order to melt or boil a substance. So you'll have higher melting and boiling points. So what this means for us is that the melting and boiling points increase from nonpolar, very low attractions, very easily to increase the distance between molecules, to intermediate polar, to on the very high end ionic compounds with lots of attraction, so it's very difficult to increase the distance to melt or boil the compound. Okay, solubility in water. Water is a polar compound. Let me draw a Lewis dot structure of water here. Here's water. It has this kind of V-shaped arrangement because of its lone pairs up there. The oxygen is more electronegative than the hydrogen, so it is pulling the electrons in this bond towards itself. So the oxygen end of this molecule is partially negative, and the hydrogen end of this is partially positive. Since it has a partial negative side and a partial positive side, meaning that it's polar, it's attracted to other charged compounds, which make them soluble. The water molecules can carry them away, which results in them being dissolved. So ionic and polar compounds are soluble, whereas non-polar compounds are not. So here's an ionic compound. It's made of positive and negative ions. You can see here the red is representing oxygen atoms, and they are partially negative, so they are attracted to positive ions, whereas the hydrogen atoms, the white, are partially positive, so they are attracted to negative ions. So basically the water molecules can deconstruct the ionic crystal and dissolve it away. Polar compounds, because there are bonds that are shared, they're not broken up. However, because they've got a positive end and a negative end, water can still dissolve them by the positive end being attracted to the partially negative oxygens, and the negative pole being attracted to the partially positive hydrogens. The last property, before we return to what causes intermolecular forces, that I want to talk about is conductivity. And it works in a very similar way to solubility. Electricity requires charges that can move, because electricity is simply the transportation of negative charges. So things that with charges, if they can't move, so ionic compounds have charged ions in them, but in the solid state those ions are held in place by the crystal, or covalent compounds that lack any charges are insulators because the atoms can't move freely or they lack any charges. What can conduct electricity are liquid ionic compounds. So if you either melt, or what tends to be easier because ionic compounds have such high melting points, is simply to dissolve them. Now those positive and negative charges are free to move about in the liquid state, so they can conduct. as well as polar compounds to a lesser degree, because instead of fully positive charges, they have partial positive and partial negative. So they can conduct, but to a significantly lesser degree. Okay, so if we were doing this in school, this is where we would have ended and started a new day. So just a quick review here. In previous lessons, we learned the basics of intermolecular forces. Ionic is at the highest end of intermolecular forces, and nonpolar covalent is at the lowest end, with polar covalent in between. We also looked at their properties. Higher intermolecular forces produces higher melting points, higher boiling points. They tend to be brittle, they tend to be soluble, and they can conduct electricity in the liquid state. We also looked at electronegativity differences to identify polar bonds, and we like to draw what is known as a dipole arrow. Sort of works like a vector, which indicates the positive, partially positive side of the bond, the lower electronegative atom, and the partially negative side of the bond, so the arrow is pointing which way the electrons are pulled towards the atom with the higher electronegativity. Okay, now here's one of the really, really difficult things for many students, which just because a molecule contains polar bonds, it may be nonpolar. And what you have to do to resolve this is you have to look at the molecular geometry. So we're going to look at two compounds where every bond is polar, and that's CF4 and CH3F. So carbon tetrafluoride and what is known as fluoromethane. And so for each of these are the Lewis dot structures that you should have drawn, and they both result in geometries that you would call AB4, because we have a central atom and 4 outside atoms. Every bond of these is going to be polar, so here's the electronegativity difference between carbon and hydrogen. Here's the electronegativity difference between carbon and fluorine, so both of these fall into the polar camp. However, these are not equally polar. Carbon-fluorine bond is much more polar, and you can see that because we have a much higher electronegativity difference. What this means is even though they have all polar bonds, only one of the molecules is polar as a whole. So CF4, I've drawn the dipoles here. This is my best 3D construction. We're trying to show that one of these fluorines is coming out towards you, and one of them is going back behind. I pulled in these 3D molecules, which are pretty neat. I like to pull them up and sort of turn and look at them. So hopefully you can see from that you have one molecule that comes out of the plane towards you, one molecule that goes back behind the plane, and these molecules are in the two-dimensional plane. So let's send you back. There you go. And this guy, we can look at it. You've got the 3 hydrogens and the 1 fluorine. Again, you have one bond that comes out towards you, one bond that recedes back, and 2 bonds that are in the plane there. So these are pretty cool. I like to play with them, especially here, because woo, so much fun. If only this would let me like rotate them, that would be really awesome. So back to where we were. I've drawn in the dipoles for carbon tetrafluoride. They are all equal because the value of each of these dipoles Whoa! That's not what I wanted to do. My finger caught the screen. Let's try that again. The value of each of these dipoles is 1.5. So this is like having a four-way tug of war where all four teams are spread out symmetrically and they are all equally strong, so it's just going to be a four-way tie. So there is no net dipole, and that's a key word. In CH4, there is no net dipole, so this molecule is nonpolar. In fluoromethane, the dipoles are not symmetric. The CF dipole is much stronger because remember we're talking about 0.4 versus 1.5. And so I've indicated that by making that arrow much, much longer. So these dipoles are not symmetric. This would be like having our four-way tug of war, but three of the teams are rather weak. One of the teams is very strong, and so we are going to have a net dipole in this, and the electrons are going to be pulled towards this fluorine atom. So this is going to be partially negative near the fluorine and partially positive on the opposite side of the atom. So this is a polar molecule. Let's consider another example. Here's another Lewis dot structure that you have probably drawn before, NH3. Again, we have all polar bonds, and they are now in this kind of pyramidal geometry. So let's pull this guy out here. So they all get angled down somewhat, and that's because you have this lone pair up on top of this that's not shown here because it's not a bond, but it is taking up real estate and forcing all of these down. So we have three equally polar bonds. So this isn't like the case of the CH3F where one polar bond was stronger than the others. These are all equivalent bonds. However, our geometry is not symmetrical because we have this fourth side that is a lone pair, and it's pushing all of the other ones. They're all pointing down. So the net dipole on this, they're all pointing down, so we are net negative there and net positive here. So we do have a polar molecule. So the take-home message, and here's the important part, to decide if an entire molecule, and that's the key thing, not just individual bonds, but the entire molecule is polar, you must figure out the geometry and see if the dipoles are symmetric. And here's a very, very quick and dirty way to figure out if a geometry is symmetric. To be symmetric, all of your bonds have to be identical. So CH3F failed this because the H and the F, those are two different kinds of bonds, so those bonds are not identical. They have unequal dipoles. And this one passed that test. However, it did not pass the no lone pairs. Even if all of your bonds are identical, like in NH3, you also have to have no lone pairs. So no geometries with, we would call this one A, B, 3, E. So no geometries with lone pairs, because those lone pairs break up your symmetry because they're going to take up real estate that isn't a bond. So take-home message here, you have to see if the dipoles are symmetric, and to be symmetric you have to meet these two things. Your bonds have to be identical, and there have to be no lone pairs. So only if an entire molecule is polar will it have the higher intermolecular forces caused by polar covalent bonds. So the things like high boiling point and high melting point. If the molecule is polar, it is said to have dipole-dipole forces. So if I draw a water molecule here, actually let's not do a water molecule because we're going to talk about those specifically later. Let's do a formaldehyde molecule here. The dipole arrows on this are as follows. So we have a net negative here and a net positive. So when I line these molecules up, the positive side of one formaldehyde and the negative side of another formaldehyde are attracted to each other. So there is some attraction. It's not a bond, but we are going to have some attraction producing greater IMFs. And this, because these are two polar molecules, is called dipole-dipole interaction. So, and that comes from, we have two things that are polar. So dipole-dipole. I scribbled out water because water is actually a special case of particularly strong dipole-dipole forces that occur in molecules containing HF bonds, HO bonds, and HN bonds. These bonds all have very large electronegativity differences, so they're a little bit closer to being like an ionic bond. So these are just like polar covalent on steroids, especially strong polar covalent. So things with hydrogen bonding have significantly higher intermolecular forces than would otherwise be predicted. So we will spend a lot of time later talking about the special properties of water compared to similar substances, and that is because it has this extra special form of very strong polar bonds, and they're so much stronger that we give them a separate name, and it's referred to as hydrogen bonding. So you just need to look for the presence of these three bonds. Okay, last one. This is a bit of a special case. We will not see it too often because it requires two separate substances. It requires a polar and a non-polar substance. And this is what we call an induced dipole. You might have heard the term induced before. It means to cause, like in induced labor. And so what we have here, if I have a non-polar molecule, I don't know, let's say CH4, just an ordinary non-polar molecule, and it comes in contact with a polar molecule, I don't know, let's say water. Water has a permanent dipole that we talked about already, partially negative on the oxygen, partially positive on the hydrogen. So when these two come in contact, this negative charge on the partial negative charge on the oxygen is going to repel the electrons in this, so that the electrons are going to run away from these bonds over to the other side because opposite charges attract, and it is going to temporarily induce a weak dipole in an otherwise nonpolar compound. So while these two are in close proximity, now we can have some attractive forces. But as soon as these molecules drift apart, this is going to go back to just an ordinary nonpolar compound, and the attractions will disappear. So these aren't as strong because they're temporary only when these are near each other. It's sort of like when you rub a balloon against your hair to get some static electricity. It builds up a charge. Then when you hold it near other objects like the wall, it can temporarily cling to them because it induces a charge in things nearby. And the last and the weakest of all the intermolecular forces are what is known as London dispersion forces. In very old textbooks, you may see these known as van der Waals forces. I just like to write a Dutch name, and this shows up on one of the lab papers that I use. So, also known as van der Waals interactions. These are the only thing going for nonpolar molecules. So, to have London dispersion forces, these are always present in any kind of molecules, but they are the only thing that are present in nonpolar molecules. And these just happen because randomly, as the electrons are going around an atom, they might all end up on one side. And this is going to cause a temporary dipole. So if I draw my nonpolar molecule again, there are electrons involved in these bonds that are going back and forth between these atoms. This is a symmetric atom, so all the dipoles cancel out, so it's nonpolar. But randomly, perhaps all the electrons, for some random reason, happen to line up all on this side of the atom. And then that means there's going to be a lack of electrons randomly on the other side. And that will temporarily induce a dipole in its neighboring molecule. But these are random and are very temporary, and so this is the weakest of all the intermolecular forces. I will say, though, the more electrons you have in an atom, the stronger the London dispersion forces, because the more electrons you have, that's like buying more lottery tickets, so there are greater odds of having an imbalance of electrons on either side. So that increases your odds of having these random dipoles. Store that in your little goldfish brains for one of the labs that we will be doing later. You'll need that in order to break the tie between two compounds that are both nonpolar. We will finish up here with a kind of flowchart, because I love flowcharts, about how to identify the intermolecular force that you have present. Okay, the first question, figuring out if you have an ionic compound or a covalent compound. Is it only made of nonmetals? If your answer is no, you have an ionic attraction, and that is number one strongest intermolecular force. Next, if you are only made of nonmetals, so you are some type of covalent, the first thing that we need to look for is the presence of those especially strong polar bonds, HF, HO, or HN. If those are present, you are going to have hydrogen bonding, which is the number two in terms of intermolecular strength. Okay? Now we need to check to see if you just have ordinary polar bonds. So check to see if you have that. Use your electronegativity differences. If you have no polar bonds, regardless of what the geometry is, no polar bonds means you are nonpolar. So you are London dispersion, which is the weakest by far. Okay. Now, if you have polar bonds, there's still a possibility that they cancel each other out, resulting in a non-polar molecule as a whole. So you need to ask yourself, is the molecule symmetric? And remember, that means identical outer atoms in a geometry without any lone pairs. So if you are symmetric, even if polar bonds are present, the molecule as a whole is nonpolar, London dispersion. If it is not symmetric, you are going to have dipole-dipole interactions. You have a polar molecule, dipole-dipole, number 3. All right, this wraps this up. It's a little bit lengthy, but it's a very touchy subject, so I hope this is some assistance to you.